Hello, everyone, and welcome to my channel. This is an educational channel, and we look at theories of everything that have inspired me and captured my imagination. Things that have helped me with my paradigm shifting, my great awakening, work in progress, and today is our 455th video on the reciprocal system of theory from Dewey B. Larson. Mr. Larson arrived at his two fundamental postulates in 1959, two sentences about how he believed the universe operated, and then he derived, through a process of deduction, at a theoretical universe. If this, then that, if this, then that, and took his two postulates and elaborated them into a whole full-blown theory of everything, to the extent that he could. Obviously, he's not going to be able to put it into, that kind of detail, just one guy, but he tried to, move his theory into many different subjects. And then he compared his theoretical universe with that of the legacy scientists, their measurements, their scientific tables that they had compiled from laboratory experiments. And in particular, we're looking at one of his books on chemistry called Basic Properties of Matter. And we're about to start chapter 7 on temperature relations. And this is very interesting stuff, in my opinion, although maybe I'm just being a nerd about it. Just the idea that every atom or molecule, what he calls a thermal group or thermal unit, every atom or molecule has its own temperature. And they all fit together. So he boils it down to that kind of detail. And then kind of extrapolates for, obviously we're not really measuring one at a time. We're measuring, bazillions of them. And so you have to use statistics, averaging. Now, basically, Larson's reciprocal system is also, you can also call it the universe of motion. He was one, not the first, but the first really successful person to propose a universe built on motion, not matter like the ancient Greeks, or not energy like Einstein or Heisenberg tried to do, but on motion. And in particular, Larson built upon what he calls a scalar motion. Scalar motion is magnitude only. It has a magnitude, but it has no specific direction. It's not like velocity. Velocity is, in a particular direction. The motion is going in a particular direction. You can envision a scalar motion if you take a balloon and you put dots on it with a magic marker. You blow up the balloon, all the dots will be moving away from each other. Every dot will be moving in every direction, away from every other dot. So there is no specific direction involved. The directions are all, kind of spread out. Every dot is moving away from every other dot. Same is true if you suck in the balloon and it contracts, then all the dots will be moving toward each other. And it'll actually appear as if you abstract it and you pick a dot and you say, we're going to pretend that this dot is motionless. So you assign a reference point. Then it will appear as if all the other dots are being attracted by that first dot, and that that dot is emitting a force field of attraction, and all the other dots are being pulled toward it. But that is not the case. Every dot is pursuing its own course. But when you choose one as a reference point, then it makes it appear as if there is a force. Larson calls that outward movement of the balloon the progression, and the inward movement is called gravitation. Now, Larson's first postulate is where the work gets done, and that is basically the universe is composed entirely of one component, motion. And motion exists in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. I'm going to try to move quickly through this, but basically that last part, that's where we get the name of the reciprocal system. Motion has 2 reciprocal aspects, space and time. You can see that in the most basic kind of motion that we know of, speed. The bike is moving 10 miles per hour. 10 miles of space in 1 hour of time, space over time. So speed is space over time. That is a reciprocal relationship between space and time. You can have that illustrated if you double the speed. You can say, now the bike is moving 20 miles per hour. Or you can also say, now the bike is moving 10 miles per half hour. You can multiply the space or you can divide the time. That is reciprocity, a reciprocal relationship. So it holds true for at least for speed. But Larson extrapolates and he applies that to all forms of scientific phenomena, including matter, energy, force, acceleration, pressure, electrical charge, magnetic flux, permeability, surface tension, power. All of these things are all fractions with space or time as the numerator and time or space as the denominator, as a reciprocal relationship. With the caveat also from that first postulate that time and space come, and motion, all have 3 dimensions. And when you do other permutations, they can even be greater than 3 dimensions. So you can have a relationship like density. Density is time to the 3rd power over space to the 6th power. The reason why is that density is matter per volume. So matter is time to the 3rd power over space to the 3rd power. And density and volume is space to the 3rd power. So when you multiply those out, you get time to the 3rd over space to the 6th. Pressure is time over space to the 4th power. Acceleration is space over time to the 2nd power, and so on and so forth. So this serves as a beautiful system, better than the MKS system of determining units for sure, because it only has 2 variables instead of 3. And that's a great way to get started. Now, what you have, Larson sets this up based on kind of on reference points. You have that, what you call a scalar reference point, a natural reference system, the outward movement of that expanding balloon. And then you have a spatial reference system and a temporal reference system. These are stationary reference systems. And these are the process, from the process of abstraction and gravitation. If you are in a gravitationally bound system, you will perceive 3 dimensions. In our particular case, 3 dimensions of space in a still frame, just like we kind of walk through on our daily, in our daily lives. We see space as being 3-dimensional and stationary, and we are moving through it. And events are unfolding in time as time gets later and later and later. This is a vectorial space, what Larson calls coordinate space, XYZ coordinates, and clock time. So the clock is still progressing. It's still moving in a scalar manner. It's always getting later and later and later, but in no specific direction. Now, extrapolating by the reciprocal relationship, there is also a location in the universe where you would have 3 dimensions of time in a still frame, and you would have progressing space or scalar flow of space. Space is always getting farther and farther and farther apart, and you have coordinates in time. So that is what Larson calls the temporal reference system. And then you have this discrete unit postulate. Space, time, and motion come only in discrete units. You have to have a full unit of space in order to have space. It's kind of like walking over to the apple tree. Someone tells you, bring me back 2/3 of an apple. You can't do it. You know, it's either a full apple or it's nothing. I mean, once you get the apple, then you can chop it in half. But they come in full pieces, in full units. And space, time, and motion do the same. So you have a minimum unit of space, a minimum unit of time, and a minimum unit of motion, which is speed, one space over time, 1 unit of space in 1 unit of time. Larson calls that unit speed. 1 unit of space and 1 unit of time, and that is actually the speed of light. So the speed of light is unit speed, and this is the speed of the progression. The progression is always moving outward in all directions at the rate of 1 unit of space per 1 unit of time, or the speed of light. Larson refers to that as the progression of the natural reference system. And this is the background of the universe of motion. Whereas the background that we normally see is this 3 dimensions of space in a still frame, that's the static background. The actual background that the universe conforms to and where Larson makes his measurements from is what he calls his 0 point or null point, the progression of the natural reference system. This is the neutral point of the universe. And you have to be able to accept this to accept a universe of motion, that you can have motion without anything moving. This motion outward at the speed of light comes before anything that is moving, and it is eternal and omnipresent. It's occurring at all locations, at all times. Or you could say at all times and all spaces. And that means that half the universe is moving slower than the speed of light. Larson calls that the material sector, and that's where you have your spatial reference system. And you also have half the universe that is moving faster than the speed of light. Larson refers to that as the cosmic sector, and that's where you have your temporal reference system. And again, they are reciprocals of one another. And when you cross that speed of light boundary, you have to invert the rules and interchange the roles of space and time. Now, within both the material sector and the cosmic sector, by the way, the cosmic sector is totally unknown to science, and they think that that is blasphemy. Einstein said that the speed of light is the maximum speed of the universe. So he is only really accounting for half the universe, half of Larson's universe. Now, within both the material and the cosmic sector, you have subregions that have to do with the discrete unit postulate. If you don't have a full unit of space, say if you have an atom, 2 atoms, and they approach each other, and they get to 1 unit of space apart, then they can't get any closer because you have to have a full unit. And so they are a full unit apart. You can't get any closer in space. What happens instead is it moves into what Larson calls the time region. Within 1 unit of space, you don't have space. because of the discrete unit postulate. So you only have time, because the universe is made out of space and time only, motion. And so it's got to be one or the other or both. If it's not space, it must be time. Larson calls that the time region. And within the time region, what happens to those particles is that they move outward in time. Moving outward in time by the reciprocal postulate is the equivalent of moving inward in space, which is what we see it as. We see it as they are moving inward in space. We're really seeing equivalent space. They are really moving together, moving away from each other, outward in time. We see it as inward in space. But we see it in a distortion, because when we look across a sector boundary, we look into a different sector or region of the universe, we have to reduce what we see by what he calls the interregional ratio, which is kind of what is lost in the translation when you're looking across a boundary. And then we also see this region, this equivalent space, as a second power entity instead of a first power entity. So we have to take that into account. And so this time region is really the realm of, your atomic and molecular, your microscopic interactions. Larson's unit of space is approximately 2/millionths of an inch. So it's actually very big compared to the size of an atom, but it's, definitely microscopic. The unit of time is 1.5 times 10 to the minus 16 seconds, and that's infinitesimally small. And that comes into play in the cosmic sector. When you don't have a full unit of time, then all the interactions of the cosmic atoms and cosmic molecules are occurring in the space region. And the rules invert again when you cross those boundaries. And now the progression is moving inward in equivalent space, and gravitation is moving outward in equivalent space, or in equivalent time in the cosmic sector. Atoms are formed by taking that progression, that outward natural reference system, outward motion at the speed of light in all directions. That is the source of everything. And you can turn that source into matter by first reversing it. Remember, it is 3 dimensions. So you have to reverse it, and then that is what's called a photon. And then when you take that photon and you rotate it, then you get a particle. And then when you combine 2 particles with 2 photons, you will eventually get to an atom. An atom is a combination of 3 different motions. 3 different rotations, 2 two-dimensional rotations that alternate, and 1 optional 1-dimensional rotation in the opposite direction that is can be 0 in the noble gases, and in other matter it is either positive or negative, really depending on whether you are electropositive or electronegative. And so Larson's periodic table is based on those concepts, and that is where he derives his equations for things like the specific heat and the melting point and the compressibility and other aspects that he, basic properties of matter that he covers here in this book. So let's start here at chapter 7 on temperature relations. Now, this is somewhat of a detailed study, and so you probably aren't going to understand much of all of it, but just let it wash over you. See if you can glean a few concepts to what you've just learned, and learning Larson is like a detective story. You have to just kind of piece it together, pick up breadcrumbs as you go along, and really suspend your disbelief, because he can say a bunch of things that that are going to fly in the face of the mainstream viewpoint that you probably picked up in high school or college when you were taking a chemistry class or whatever. You need to put that aside and recognize that these experts out there, they may pretend like they tell you that they've got it all figured out, but the ones that are really good at what they're doing, they know that they don't have it figured out. They know that they don't have a full-blown theory of everything, a foundation to establish what they're working on, and that their knowledge is all totally fragmented. And so they know, the best ones know that they really do need some help. And so unfortunately, there's a lot of them that think that they have it all figured out, and so there's no need to listen to something like this. There's plenty of need for Larson's theory to be incorporated into science. And if you study the history of science, you will know that all of the major revolutions in science come from outside the field. Almost by definition, in order to be a scientist, you have to pretty much play ball with the current paradigm. And if you even entertain anything outside of that paradigm, you jeopardize your status within the paradigm. And so, I can imagine that a century from now, this will be the paradigm, and everybody will need to know this, because it's not only in chemistry, it's in all fields. If you learn how it applies to chemistry, you learn how it applies to just about everything, or to absolutely everything. It still takes some work to figure out how it applies, but Larson gives you the foothold here. Okay, so Chapter 7, Temperature Relations. As explained in introducing the comparisons of the theoretical specific heats with experimental results, the curves that we went over last chapter verify only the specific heat pattern, the temperature scale of each curve being adjusted to the empirical results. In order to complete the definition of the curves, we will now turn our attention to the temperature relations. All of the distinctive properties of the different kinds of matter are determined by the rotational displacements of the atoms. These are the three numbers, the two-dimensional rotations that I was referring to, the rotational displacements of the atoms. He calls them displacements because they're really not motions. Because you have the progression. The progression is the primary motion, and these are just displacements from that progression. They're not independent motions of themselves. They are displacements from that original motion. So, by the rotational displacements of the atoms of which these substances are composed, and by the way in which the displacements enter into the various physical phenomena. As stated in Volume 1, the behavior characteristics or properties of the elements are functions of their respective displacements. Some are related to the total net effective displacement. Some are related to the electric displacement, which is the one-dimensional. Others to the magnetic displacement, which are the two-dimensionals. While still others follow a more complex pattern. For instance, valence, or chemical combining power, is determined by either the electric displacement or one of the magnetic displacements, while the interatomic distance is affected by both the electric and magnetic displacements, but in different ways. The great variety of physical phenomena and the many different ways in which different substances participate in these phenomena result from the extension of this more complex pattern of behavior to a still greater degree of complexity. One of these more complex patterns was examined in Chapter 4, where we found that the response of the solid structure to compression is related to the cross-section against which the pressure is exerted. In this case, pressure is force per area. In Larson's system, force is time over space to the second power, and area is space to the second power. So pressure is time over space to the fourth power, but it really is a force per area. So when you have compression, which actually comes from the progression of the natural reference system, because it's inward in the time region, because it's reversed, that internal pressure or an external pressure is a force per area, where the atom is three-dimensional. And so the force is really dependent on how it's actually hitting that atom, because that atom could be oriented in a certain way where that force gets its maximum pressure, or it could be oriented in a way where that force, which is only two-dimensional, is less, less of a cross-section, and it's not being affected as much. So that's kind of what he's talking about there. The numerical magnitude involved in this relation is determined by the product of the effective cross-sectional factors, together with the number of rotational units that participate in the action, a magnitude that determines the force per unit of the cross-section. Inasmuch as one of the dimensions of the cross-section may take either the effective magnetic displacement, represented by the symbol B in the earlier discussion, or the electric displacement, represented by the symbol C. Two new symbols were introduced for the purposes of the compressibility chapter. The symbol Z to represent the second magnetic displacement entering into the cross-section, which is either A or B. Now just keep in mind that's Larson, his periodic table. The three numbers, A, B, and C. Primary two-dimensional rotation, secondary two-dimensional rotation, and then the optional three-dimensional or one-dimensional rotation in the opposite direction. And so these numbers go into the compressibility equation, but he uses A, Z, and Y because the A is still there, but the Z is either B or C, and the symbol Y to represent the number of effective rotational units, which is related to the third of the displacements. So the ABC factors were thus represented in the form A, Z, Y. The values of these factors relative to the positions of the elements in the periodic table follow the same general pattern in application to specific heat as in compressibility, and most of the individual values are either close to those applying to compressibility or systematically related to those values. We will therefore retain the AZY symbols as a means of emphasizing the similarity. But the nature of the thermal relations is quite different from that of the relations that apply to compressibility. The temperature is not related to a cross-section. It is determined by the total net rotation. Consequently, instead of the product AZY of the effective rotational factors, the numerical magnitude defining the temperature scale of the thermal relations is the scalar sum, A plus Z plus Y, of these rotational values. So Larson determined through deduction that pressure is related to A times Z times Y, while temperature is related to A plus Z plus Y. This kind of a quantity is quite foreign in conventional physics. The scalar aspect of vectorial motion is recognized, that is, speed is distinguished from velocity, But orthodox physical thought does not recognize the existence of motion that is inherently scalar. In the universe of motion defined by the postulates of the reciprocal system of theory, on the other hand, all of the basic motions are inherently scalar. Vectorial motions can exist only as additions to certain kinds of combinations of the basic scalar motions. That would be, your spatial and your temporal reference systems. But the natural reference system is a scalar reference system. That's your expanding balloon. Scalar motion in one dimension, when seen in the context of a stationary spatial reference system, has many properties in common with vectorial motion. This no doubt accounts for the failure of previous investigators to recognize its existence. So, if you are in your spatial reference system, which we are, you can see this motion of an expanding balloon, and really on a balloon, and it appears to be like a vectorial motion. It's not really until you really consider it that you see that it's actually a scalar motion. And this is the same motion that all of our distant galaxies participate in. All of the distant galaxies are all moving away from each other. So it's not just like a balloon. It also includes, astronomical phenomena. Now that expansion, that's what the Big Bang is being used to answer. But that is not the right application, because if it's a Big Bang, that means that there is an initial point from which they all kind of blew up and expanded, and that would put us at that center. And if we're not going to go with the pre-Copernican view of a geocentric worldview, we have to assume that our galaxy is also participating in this idea of moving away from all other galaxies. So our galaxy would also be on the fabric of that surface of the balloon. But when motion extends into more than one dimension, there are major differences in the way that these two types of motion present themselves or do not present themselves to observation. Any number of separate vectorial motions of a point can be combined into a single resultant, and the position of the point at any specified time can be represented in a spatial system of reference. Okay, we're going to stop there. Thanks for tuning in.